Hello everyone, so today we'll be talking about deep feedback models. This is something that I've been really interested through the past 2 years as I worked as a postdoc researcher at INESC-ID. So in this presentation we'll first go over what is feedback, then how can we implement this operation in deep neural networks, how can we ensure that these models are stable, the complexity of them, and how can we extrapolate this operation to the spatial axis. So, to understand feedback, I think it's important to understand what is feed-forward first. So, in feed-forward models, imagine that you have the representation of a beautiful poodle. This beautiful poodle comes as an image with height h, with W and C channels. The C can be RGB for the case of 3 channels, of course. And the stimulus is fed to a neural network, which maps this to a lower dimensional representation with N filters. In this latent representation, after F, this is forwarded to a classification head, G, which maps this representation to a space with dimension L. And the output of the model is going to be a state vector y hat, which represents the target associated with the specific stimulus of a beautiful poodle. So, feedback is very similar in terms of neurocircuitry, but of course one thing that changes is that we are going to split the latent representation and feed back to the input of the neural network F prime. So, we are going to have additional neurons and concatenate these neurons to the input with the stimulus representation. Naturally, you are going to accommodate a new neural network F prime with B neurons for this feedback operation. Of course, that this operation is very minimal, but the changes that it makes are very high. So, on the one hand, we have a static system, which is the feed-forward model, because whenever we have the same input and the same parameters, we will always have the same output stimulus. And on the other side, we have feedback. Since we have a feedback loop, we can unroll this feedback in time, and this makes for different predictions as time evolves. Another thing that makes feedback different from feed-forward is that feedback is able to predict instances based on internal state, not only the stimulus, and this is very aligned with neuroscience theories that what our perception of something is conditioned on our expectation at that specific moment. Feedback is also biologically plausible. So the human brain is a dynamical system. It changes its predictions in time and is able to process stimulus at different time resolutions. And this is why I think feedback is also biologically plausible, more than feed-forward. And this is very aligned with the neuroscience theory of predictive coding, which says that the human brain does not necessarily fire according to a specific representation. It fires according to the difference between the stimulus and the internal representation that it has. And this is something that was introduced in 1999 by Howe et al. And published in Nature at the time. So, what is our notion of feedback? So imagine that we have a beautiful poodle again. We process these through a neural network F prime, which outputs a syringe. Now, this neural network is a neural network that belongs to a veterinarian doctor. He's been working all day doing surgeries and administering vaccines, and he cannot see anything else in front of him besides syringes. And naturally, that if his perception or if his expectation is going to be syringes, his perception is also going to be a syringe. Now, this veterinarian doctor is not just any doctor. He is a doctor which has feedback loops, so he's going to be able to split the latent representation and concatenate it back to the input, and you'll have another chance to make the prediction. And it's very small, the change, but in the beginning he'll have the poodle representation appearing in its internal state. The perception that it has, it's still syringe, but it's going to change in time. And as this process of feedback repeats more, it will come to a converged state where the internal representation is perfectly aligned with the stimulus that it receives of the beautiful poodle, and life is beautiful again. So what we are proposing in this study is that we are going to define feedback as a decision differential equation, which is defined by a derivative. So the derivative is a condition on the internal state H multiplied by something. And that something right here is what we are going to contribute to. So H is an internal state. It has N neurons for classification, B neurons for feedback, and this is exactly the internal representation that in the previous slide we showed that changes from the syringe gradually to the representation of a poodle. So, how can we implement this in neural networks? We have this state vector H. We are going to say that this state vector is always going to be the concatenation between two vectors, so U and V. U is the vector that has N neurons, and naturally it will go to the classification head to make a prediction, and V is going to have B neurons, and it's going to be concatenated with the representation of the beautiful poodle or the input. This representation is then fed to a neural network, which we call this expression delta t to simplify our life in the forward equations. So we are going to define a system with a nonlinearity, which is present in delta t, because this neural network right here is going to be a big neural network, and it will change the representation a lot and not have a linear relation with the input. Then this is processed by the exponential of a matrix P, and this is going to give us the derivative of our system. We are going to propose a solution, so we perform Euler discretization, and our solution for the next steps is going to be H plus delta t processed by the exponential of the matrix P. Now, what does this mean in terms of circuitry? So bear with me. Again, we have the beautiful poodle representation. We feed it back to the neural network. The neural network is going to give an error signal, which is the difference between the internal state and the stimulus. Then this is processed by the exponential of a matrix P. We aggregate these in a state vector, and this state vector is going to have the internal representation. Then this vector is split into one part goes to the classification head to give a decision, and the other part is going to be upsampled, taken the softmax, and concatenated to the stimulus representation of the beautiful poodle. Okay, so to test this, we first generated an artificial data sets with triangles, and we wanted to assess two things, so robustness and generalization. To assess robustness, we defined a random variable, epsilon, which is going to be a Gaussian centered in 0, and we are going to change the parameter of noise from 0 to 10. Then, to assess the generalization ability, we are going to define a variable which we name examples per class, but in this setting right here of segmentation, this is going to be the training size, and this is going to change from 1 to 10. We are going to minimize the negative log likelihood, so please ignore this L right here. So we are going to have a training set that goes from instance 0 to instance D, and we are going to perturb the input with Gaussian noise. So these are the qualitative results that we have. So in the y-axis, we have the noise changing from 0 to 8. So here we have the sigma. And on the horizontal axis, we have a set of columns. So in the first column, we have the input. You can see that with 0 noise, it is a perfect image with no perturbation at all. And as we increase the level of noise, we can start seeing that we do not see the triangle that is in this image because the noise is too high even for us. The second to the seventh column are going to be the multiple predictions at the different time steps made by the feedback model. The second to last column is going to be the feed-forward prediction, and the last column is going to be the ground truth. So we can clearly see that in the first few levels of noise, the predictions made by the feedback and the feed-forward models are very similar, so they can extract a meaningful pattern from the perturbed and non-perturbed data. And as we increase the levels of noise, we can start seeing that the feed-forward model especially starts to get a degraded performance really quickly. Whereas the feedback is able to extract at least a meaningful pattern that matches the ground truth that we have in the last column. I want you to pay special attention to the 7th and the 5th levels of noise, where I think there is a really interesting phenomena where in the first iteration of feedback, you can see that, for instance, here in the 7th, you don't see the triangle in the first iteration, but as you give it more time, it converges to a meaningful pattern. And something similar happens here in the 5th level of noise, which is that the background pixels are being predicted as triangles, and they should not. And as you give it more time, it has a more refined prediction of the segmentation. So here we have the F1 score for this task of segmentation. So on the left you have the noise changing, and the y-axis is the F1 score. You can see that in cyan is the performance of the feed-forward model, which degrades really quickly. And in contrast, the feedback model is able to perform above random for all of the levels of noise that we tested. On the right you have the same, but evaluated for the size of the training set. You can see that with 2 instances the feedback model is able to perform above random, whereas the feed-forward model needs twice the number of instances to generalize in this setting. Now that we proved that these models are able to generalize and be robust, and this is something that are 2 traits that differentiate human intelligence from artificial intelligence, and I think it's really neat, we can start talking about how we can make sure that these models are stable so that we can test them in large-scale data sets. So bear with me. So we have again the system equation, so the age plus the neural network delta and processed by the matrix of exponential of p. So to make sure that these models are stable, we are going to define a matrix p with real negative eigenvalues. So you're going to perform the eigendecomposition of p into a matrix of a set of eigenvectors, a matrix sigma whose diagonal is going to be the eigenvalues and the inverse of q. We set sigma such that it is the negative of the identity matrix, and our system equation becomes h plus the neural network dot product with q. We exponentiate only the eigenvalues because this is something that you can do, and we also multiply it back to the original space. In this setting right here, we are not, so the q and the inverse of q are not going to correspond necessarily to the inverse of each other, so we are going to train them separately. And we are not computing gradients for the sigma because we want to ensure that the system always converges, and by training sigma, we may run the risk of some eigenvalues becoming positive, and then the system will diverge in time. So, to prove that the system is stable under this formulation, we are plotting the principal component of the output vector representation of the neural network of a feedback model, and we can see that as time evolves, the principal component does not change. So we are able to ensure that the system goes to is stable and converges to a specific point in equilibrium. Of course, the specific point is different for each instance, but we are able to prove this. Now, we wanted to assess if the exponential decay and the softmax contributed to the convergence of this system. So they do, but before that, we observed that they have the same performance in terms of F1 score in this task, but on the other hand, the principal component is always changing in time. So it does not stabilize, does not arrive to a specific equilibrium point, and this can hinder the model in large-scale data, because if we train with a lot of iterations, then the gradients might explode or vanish depending on the case. So this is something that hurts us. Here in the tiny image net, we have the internal trajectories made by the feedback model. So we have trajectories of standard poodles and syringes, so you can clearly see that they are separated. But what I really want you to notice is that so here in the center you have the initial state where they all come from, and the first step is always bigger than the second step, and the second step is always bigger than the third step. So this is the phenomena that we are observing of the model converging to a specific state. Now, at inference time, what exponential decay allows is that we ensure that the model is going to converge to a specific point. We don't know that point, of course, because we do not have a proof. We just know that experimentally it converges. But at training time, this is something really neat happens, which is that we are able to bound the gradients. So the gradients is going to be a sum of a nonlinearity from 0. It can go to infinity, of course, but due to the nature of the exponential of the matrix P having real negative eigenvalues, we are able to ensure that the gradients are bound. Now, although we have exponential decay, we need to ensure one more thing to make sure that these models are able to learn in large-scale datasets. So we still observe that we were having exploding and vanishing gradients when you were learning on the ImageNet dataset, and this is because so this is a system equation, right? When we map this instance to the spectral space, we don't ensure that these matrix Q maintain the norm of this vector delta, of course. So what we are going to do is that we are going to define an orthogonal matrix of size n plus b, and every time that we do a gradient update on Q, we are going to have a non-orthogonal matrix. So think of Q as it belongs to the orthogonal matrix space. You move it to a non-orthogonal representation, and we are going to apply the Gram-Schmidt on that non-orthogonal representation, decompose the matrix into two matrices, Q, which is orthogonal, and an upper triangular matrix R. And we retrieve Q from here. So we move it from an orthogonal to non-orthogonal and correct it back again to non-orthogonal. Now, this allowed us to test our model in large-scale datasets such as the ImageNet case, and here you can see the impact of different levels of noise on the accuracy of a ResNet 18 in the ImageNet dataset at a lower resolution of 64 by 64 pixels. And for all of the levels of noise that we tested, the feedback in orange dominates the performance of the feed-forward model. We also tested these with different numbers of examples per class, basically, and we have the examples per class in base 2, and we have the accuracy log scaled in base 10, and you can clearly see that for all of the examples per class that we tested, the feedback again dominated the performance. And I want to do special attention here to the 8 number of examples per class, where the performance of the feedback is more than 10 times greater than the feed-forward. So this is something really neat that we were able to observe in a small-scale data set of the artificial experiment, and you were able to extrapolate the same phenomena to a large-scale data set. Now, since we are observing that these models with feedback are able to learn in limited samples settings and noisy settings, we thought that it would be really nice to test it in medical imaging settings. So medical imaging settings are characterized by limited individual participation, either because there is not enough money in projects to gather people, or because the presentation of a specific disease is very limited in the population. And of course, the modalities that are recorded for different medical imaging modalities contain high levels of noise. So we compared our model, which is we denote here as a DFM ResNet 50, against other baselines. So again, we have the feed-forward ResNet 50. We have the CRBP, which is the recurrent backpropagation model, where we first put the backbone of the ResNet 50 and then we implement their convolution LSTM that they propose in their paper. You can check the references in our study and go to these studies to check in more detail what these models are. Then we have the CoreNet, which is a very known model that enrolls a network in a biologically plausible way. We have deep equilibrium models, so this is a type of implicit model that reaches an equilibrium and was proposed in 2019. And to make sure that our model, that the feedback plays a big role, and it's not just the number of iterations that matter, we also tested our model and masked the feedback when we concatenated to the input. And I want you to pay special attention. So these are different data sets from the MedMNIST database, and we gathered the 5 data sets that were the smallest. And I want you to pay special attention to the retina and the breast, which are the smaller data sets. And this is where the difference from our models to the other baselines that we compare is the biggest. We also tested them in different types of noise settings, so not just Gaussian noise, and we were able to prove that our models are competitive with the other baselines that we compared to. And specifically, we ran a t-test value, a statistical test between the masked feedback and our model. And of course, for all of the metrics that we gathered, we showed that the DFM without the masked feedback is able to perform better than with the masked feedback, and with statistical significance, of course. So this is kind of an assurance that feedback is playing a role, and it's not just by chance that we are better. In terms of complexity, here we have the baselines that we just compared to. Of course, in terms of floating point operations, the feed-forward has 4 gigas of floating points, and all of the recurrent models have 5 iterations, by the way, in this evaluation, and the feedback that we are proposing has 5 times more. This is natural, but you can see that the deep equilibrium model has more floating point operations, as well as the recurrent backpropagation model from the stable and expressive vision models papers. In terms of number of parameters, we are in comparison with the other baselines. The CRBP has a lot more. This is because I made a tweak to what they proposed. So what they propose is was meant to be a shallow model, and since I put first the ResNet 50 and then their model, of course the complexity is going to explode. In terms of batch processing, so this means the mean time of the forward and the backward pass, we have the highest value, but it's not that much bigger than the CRPP, and of course for 5 iterations is only 5 times more than the feed-forward model. Okay, finally, until now we have shown a way of doing feedback that does it pixel-wise, and of course there are tasks such as segmentation, whether neighboring pixels matter, and we thought, okay, let's define a system whose derivative is given by the convolution of the error given by a neural network and a kernel system. And the solution to these, using the Euler discretization, if you omit the normalization constant of z, is this one. The normalization constant here is just to make sure that our gradients are bounded again, because here we are going to have an impact on the size of the kernel, and we want to normalize that with z. We still make QR decomposition and set the eigenvalues to be real negative eigenvalues so that the system converges, and we tested this on the CocoStuff dataset. here we observed the same phenomena, so the feedback was able to outperform the feed-forward for all of the levels of noise that we tested. And finally, we made an ablation study where we saw what was the impact of each component that we proposed on the tiny ImageNet. And you can see that for all of the components that we proposed, exponential decay, orthogonality, and the convolution that we just introduced now, it benefits the performance of the model. So if you have any questions, please feel free to email me or drop a comment on this video. And thank you so much.